Okay, this is the second part of the lecture, tensors. If I quickly recall the previous part uh, which we did last time. So, what we did last time is that if we have a vector space V and there is a basis B, you know that a vector space can have many bases and there is also a basis B prime. So, we can relate in row vector form the basis, let me say basis B is this, B1 up to Bn, and basis B prime is from B1 prime basis vectors up to Bn prime. And we know that if there is a transformation, change of basis matrix which transforms basis B into basis B prime, then we can relate them as in this manner. B prime is actually B dot R. So, this is actually in the row vector form. And if you remember, so if we have a general vector which we can write it in this manner, Vi Bi. So, this vector, the components of this vector Vi, these are actually contravariant components, and let me say if I have a matrix V and it has a representation in B, and then if I change the basis to B prime, then this vector will have become VB prime, or we can call this V prime. So, how can I find the components? V prime will become V prime I and Bi prime. So, how can I find V prime I? So, I had discussed this in detail that V prime, which is actually V in the B prime basis, this becomes equal to VB prime will become equal to, in the form of row vector form I can write it in this manner, V dot R inverse, and in the component form I can write this V prime I is actually equal to Vi Vk this, and I will come here. So, we call these vectors contravariant vectors. Because they transform in inverse manner to the change of basis matrix. Similarly, if we had a linear functional, so from the previous lecture, you know that linear functional is actually from vector space V to some real numbers or some field on which the vector spaces is taken. So, its components actually transform according to the change of basis matrix. So, for example, this alpha prime, which is actually alpha in the basis B prime, this will become equal to alpha in the old basis multiplied by change of basis matrix. So, in component form you can write this in this manner. So, for covariant vectors we have this lower index which is subscript here, and for contravariant we have this superscript which is here. Now, in this lecture we further generalize this concept to any rank tensor. So, for example, in general this vector is actually covariant, the other one is contravariant. Now, in general we have this notation we have this notation that any vector tensor in general, that will become PQ tensor. This is contra index and this one is covariant index. So PQ tensor. So let me say we have, let me consider a 1-1 tensor. 1-1 tensor will be a tensor which has, whose P index is 1 and Q index is 1, which means it has one contravariant index and similarly it has one covariant index. So for this we take linear transformation as an example. Linear transformation. So you know that we can transform vectors with the help of linear transformations in a vector space. So let me say we have a vector space and in that vector space we have a vector v, and then let us consider this as a vector space v, vector space. It has a basis b and a basis b prime, and let me say there is a vector v basis b, and then I apply some transformation capital T on this, and I get a vector w which is also in basis b. So if you remember, in one of my videos I had explained that a transformation matrix has a representation in a specific basis in the form of a matrix. So in B basis, this transformation vector has actually TB representation. And if I change the basis, then this vector will have, this transformation will have its own representation. And I can call it T prime. It will be T and B prime basis. So that will become equal to TB1 prime TBN prime. Now the question arises, if I know a transformation in B basis, then how can I find their transformation in B prime basis? How can I relate this? Okay, so let me say if I have V vector in basis B and I apply transformation T in basis B, and I get a vector W in basis B. So in a prime basis, what will happen? I will get W prime vector, and similarly I will have the transformation here will be T prime, and the vector in that basis will be V prime. So then I can apply transformation laws to get the relation. So what is happening? W prime is T prime, V prime. Okay, so I can write this simply as W is equal to T, V, and W vector, as this is a vector is contravariant. So I know that W prime is actually equal to R inverse W. I am taking here these things in the column vector form. These are in the column vector form, CVF. So W will become, from this equation, W will become R W prime. So I can write here R W prime. This will become T, and V is also a contravariant vector. So in column vector form, I can safely write this in this manner. V will become RV prime. So W prime will become equal to R inverse T R V prime, and that's what we want. So what does this equation means? If you compare this equation, we call this equation 1, and this equation, let me call this equation 2. So what I obtain is this, that T prime is equal to R inverse T R. So this is the relation. It means the transformation matrix in the primed basis is actually having R inverse as well as R. So this is different from the previous scenarios. Previously we had either R or R inverse. This time we have both of them. So it means that one component is one index of this tensor is contravariant because of R inverse, and the other is covariant because of R. So in component form, I can write this in this manner. Let me say if I have so in component form, T prime Ij, this will become R inverse I K T K L R L J. So I am following Einstein's notation. In Einstein's notation, if an index appears two times, one time in the superscript and one time in the subscript, then that means summation. So for example, in general, if I have something like this, Ej and Bik, so it means the summation is running over this I index. Summation is running over this index, or this index, I index, which means I will have summation over I index, and there will be no summation over in the J and K index. So this is example of type 1 tensor, because I index is here contravariant, I is contravariant, and the second index, which is actually the J index, that is covariant. So one index is contravariant, the other is covariant. It means it is a 1-1 tensor. So now this was an example of a 1-1 tensor. Now I can define a tensor, that what is meant by a tensor. So now I come towards the definition of a tensor. Definition of tensor. So what is a tensor? A tensor of type PQ, tensor of type PQ is a multi-dimensional array, T I1 up to IP and J1 up to JQ, assigned to each basis of a vector space such that if the basis is changed from B to B prime through this equation, means B prime in row vector form is in this manner, then the T, then PQ tensor transform is T prime I1 up to IP and J1 up to JQ. So, this will become equal to R inverse I1, let me say K1 to R inverse IP and K P will come here, and T K1 up to Kp, just summation will go over here, and then L1 to LQ multiplied by, so actually I am writing it in the second line, but it is actually going along, so it is multiplied. So, R L1 and J1 up to R LQ and JQ. So, this is the definition of a tensor. A tensor will transform according to this equation. In the new prime basis, the transformation law will be this. So, you can see that the summation is going over these indices, those indices which are appearing up and down in the subscript and the superscript. So, the summation will actually go over them. So, for example, summation is over these indices K1 up to Kp, and then L1 is appearing here in the subscript, again it is appearing in the superscript. So, summation is actually going in over them. Okay. So, we call such a tensor of type PQ. So, it is a multidimensional array. What is meant by a multidimensional array? So, this is the definition. Let me remove this. So, a multidimensional array is, for example, if we consider a scalar. So, a scalar is actually a tensor of rank 0. Okay. And if we have a vector, so it is a single index tensor, and a vector is actually of type 1 0. And similarly, if we take a covector, which is also called a linear functional, so that is of 0 1, and if we have a linear transformation T, so it will be of type 1 1. So, this is actually a number, the scalar is a number, the vector is a single dimensional array. Similarly, covector is also a single dimensional array, and this 2 index tensor is actually a matrix, and the higher order tensors which have more than 2 indices, they are multidimensional array. For example, if they have 3 indices, let me say 1 2, so it will become a 3-dimensional array, and if they have 4 index, so it will become a 4-dimensional array. So, in general, the tensors are multidimensionals. Okay. So what is the advantage of using tensors? Why we use tensors? So tensors are actually it is the actual language of working in science such as physics, because we have in physics we want the same formula in all the different coordinate systems. So for example, in Einstein's theory of general relativity, we need tensors. Without tensors you cannot do general theory of relativity. So how can I show that a tensor gives me the same type of expression in different coordinate systems? So for example, if I take V as a vector, so it has a representation Vi, Bi, which means I'm using Einstein's summation. So how am I sure that in another coordinate system this vector will be having this type of expression V prime I Bi prime? Okay, so if we have this representation Vi Bi, so I can write this as we know that V prime is actually equal to, in column vector notation, this becomes R inverse of V. So V become R V prime. So in component form I can write this in this manner, R I K and V K, and Bi I also know that B in column vector notation can be written in this manner, B prime R B. So in component form this Bi will become equal to R inverse, because then this B will become equal to R inverse B prime. So this will become R inverse, and I will come here, L will come here, and then BL prime. So I can write this also in this manner, R I K multiplied by R inverse L I, and this will become, this is actually prime, V prime K, so V prime K and B prime L. Okay, so these R and R inverse are actually inverse matrices of each other. So I will get identity matrix, and I can write it in this impulse or delta LK, which means it will be 1 if L is equal to K. So this becomes equal to V prime L, V prime L, and as this is a summation index, so I can also write it this in this manner, V prime I, B prime I. So it is the same, but this representation is in the B prime basis. So therefore we prefer this mathematical expression to be in tensor form, so that they have same forms in different bases. So if they have a form Vi Bi, so they have the same form V prime I B prime I in a different basis. So the form should remain same. So this is an advantage of the base tensors. They have same expression in different bases or in different coordinate system, and this concept is quite frequently used, and almost everywhere this is used in the physics, especially in the general theory of relativity, and also in differential geometry.